let us talk about graphing absolute value equations on the xy or the Cartesian coordinate plane. All right, what we're talking about here would be an equation of this form right here. Y equals the absolute value of x. Now, this particular version is indeed the standard form, and I will call this the parent equation for reasons which will become painfully clear in a little bit. So here's our standard form of an absolute value equation. And let's start by just graphing this. So there's my y, there's my x. And one way to graph this is to actually plot points, right? So if I make my little table, there's x, there's y. And if x is 0, then y is 0, sure. If x is 1, the absolute value of 1 is 1, so y is 1. If x is minus 1, the absolute value of minus 1 is 1. That means y is 1. If x is 2, y is 2. If x is minus 2, then y would still be 2. Because that's what absolute value does. It makes anything inside of it positive. You already know that. So that means if I were to plot this, there's 1 point, 0, 0. There's another point at 1, 1. That would go right there. There's another point at minus 1, 1. That would go right there. There's 1, 1, minus 1, 1. 2, 2 would be out here. 2, 1, 2, 1, 2. That'd be right there. And then minus 2, 2 would be right there. So this graph looks like that. And there you go. This is your parent graph right here for that function right there. Y equals absolute value of x, whomp, whomp. Now, in general, whenever you see a graph that has a corner in it, particularly if the lines are straight, you can pretty much bet there's going to be an absolute value involved somewhere. But that's just a general thing to look at, you know, particularly at this level of math. Pretty much guaranteed that's the case. Okay, now, so here we have an absolute value. This is the parent graph, and this is pretty easy. You just plot some points, draw the points, connect the dots. A chimpanzee could do this. In fact, I saw a chimp do this at a state fair once. Okay? What we're more interested in is what happens when this gets a little more complicated. I wonder what does happen. Well, let's take a look at it. Let's draw a graph again. Here's my parent graph. And you will recall that those are the same points right there. Now let's say, just in the case of argument, that I have a graph that instead looks like this. So it's the same graph, but it's moved up 1 unit higher than it was at the start. Well, you will recall that I said that I'm going to call this the parent graph. And indeed, because everything, all the changes I'm going to make can all be related back to this parent graph. In this case, our original graph in black has now been moved up 1 unit to the blue graph. Now, every point on this graph has moved up. That one, of course, this one, everything on the entire original graph has been moved up 1. And up and down relates to the y-axis. Left and right relates to the x-axis. So that means this graph that I just drew can be written as y equals the absolute value of x plus 1. Because every value that was here has just been moved up 1. And it works the other way around too. If I were to go, say, with something like this, let's go down 1, 2 this time. Now, there's my original graph, y equals absolute value of x, okay? But this time you can see that this point, for instance, has been moved down 2 spaces. This point here, moved down 2 spaces. This point here, moved down. Every point on here has been moved down 2. So I can write that graph now as y equals the absolute value of x minus 2. And there you go. Now, what's our general truth here is that if I start with my parent graph, and I add or subtract a number outside the absolute reference, so outside the value symbol plus 1 or minus 2, that is going to move up if this is a positive number and move down if it's a negative number. That's going to take the entire graph, move it up or down if that's positive or negative. Right? Right. All right? So if I have a graph y equals the absolute value of x plus or minus b, then that moves up or down depending on what b is. Okay? So remember that. Remember that. All right? Now, let's see what happens if I do something a little different. So let's start again with our parent graph. Looks like that. Looks like that. There's our parent graph. Y equals the absolute value of x. Okay. Now, in this case, I'm going to rather take a graph, and I want to take this point that was right here and just move it over 1. So it's right there now. Okay? That means this graph, if I move the entire graph along with that point, now looks like this. And indeed, you can see that every point on this graph has now moved over 1. This point here moved over 1. This point here moved over 1. This point here that I started with, I moved it over 1. There's 1 right there. So every graph has moved over 1. Now, isn't that interesting? Now, what would be the formula, the equation for that new graph? Well, to illustrate this, let's plot a few points, shall we, of my new graph, the blue graph. Based on the picture there, you can see that when x is 1, y equals 0. Interesting. When x is 0, y now, it's up there, equals 1. When x is 2, y equals 1. Isn't that interesting? Let's see what happens when x equals minus 1. That equals minus 1. That's that point right there. That means y now equals 2. Interesting. Let's do one more. Let's say x equals 3. If x equals 3, 1, 2, 3, we follow that up. There's my point right there. Now y just equals 2. All right. Now let's look at how these numbers came about by looking at the equation. What happened there is if I subtract 1 from my x value before I apply the absolute value function, then I will get these values here. If x is 1, 1 minus 1 is 0, well then y equals 0. If x is 0, 0 minus 1 is negative 1, but the absolute value makes it a positive 1. If x is 2, 2 minus 1 is 1, absolute value of 1 is 1. If x is minus 1, minus 1 minus 1 is minus 2, and the absolute value makes it a positive 2. And if x is 3, 3 minus 2 is 3 minus 1 is 2, and the absolute value of 2 is 2. So this point that was here, and that's true of any other point on that graph, by the result of adding a negative 1 here, I've moved the entire graph in the positive direction 1 unit. A unit. And so we have another general truth here, and that is that if I take and move this graph left or right, if I move it in the positive direction, I'm adding a negative of that value. If I move it in the negative direction, in other words, left or right, I'm adding a positive. Let's look at another example. Again, let's go back to our good friend, our parent graph. Looks like that, give or take. Okay. Now, this time, I'm going to take and I'm going to move this. Start with that point right there. That'll be our target point there. We're just going to move that 2 spaces here to the left. So that point is now there. So this graph that did go there now simply has been moved over. Every point on the graph has been moved over 2 spaces. Bunk, 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 bunk. Okay? Now, based on what we saw here, then I would argue that the new formula for our new line would be x plus 2. I assert that this equation gives us our blue graph. Well, let's plot some points and see. When x is 0, okay, all right. 0 plus 2 is 2. That means y is 2. When x is 0, y is 2. Awesome. All right. Let's see what happens when x is negative 1. When x is negative 1, I have a minus 1 plus 2, which is a positive 1. So y is just 1. Look at that. That's that point right there. Okay. When x is, so this is just positive 1. When x is negative 2, now what happens? Negative 2 plus 2 is 0. Absolute value of 0 is 0. Y equals 0. That's that point right there. And we'll just do one more. When x is minus 3, minus 3 plus 2 is a negative 1. The absolute value of negative 1 is 1. So y equals 1. So you can see that every point we had on our parent graph has just been moved 2 spaces to the left to get on the blue graph. So again, my point is that if you add or subtract a number to the x value inside the parentheses, okay, that will cause the graph to move left and right. It moves left if it's a positive value, and right if it's a negative value. So it moves kind of the opposite you might think. In this case, we saw that adding a positive number moved the graph up if you add it outside the absolute value. Adding a negative number moves the entire graph down. But if you add or subtract the number inside the absolute value mark, then that moves it left or right, depending on whether it's positive or negative. And it always works in reverse, remember, so that if I add a negative number, I'm actually moving to the right in the positive direction. If I add a positive number, I'm moving to the left in the negative direction. Right? Right. So what does that mean for us? That means that we can now graph much more complicated equations just by considering what happens to our graph when we add or subtract different variables or different numbers in different places. Let's see what happens here. Let's say that I wish to graph the following equation. Y equals the absolute value of x minus 2 plus 3. Okay. Well, let me draw my Cartesian graph, of course. And I'm going to draw here my parent graph. I'm just going to dot that in because that's not a real answer here. I'm just drawing that as a give you guys a reference point. There you go. So this is the graph y equals absolute value of x. That's our parent graph. So now that we know what happens to this entire graph when I add or subtract numbers here and out there, we can see precisely what's going to happen with this. This entire graph is going to go up 3 because I've added a 3 outside the absolute value reference, and it's going to go to the right 2 because I've added a negative number or subtracted a number inside the absolute value mark. So this point that was here, okay, is now going to move over 2 to the right and up 3. Over 2 and up 1, 2, 3. That point is now right there. And every other point will now follow suit. This graph now will go like that and like that. And let's just check real quick. If x is 0, x 0 minus 2 is minus 2. The absolute value of minus 2 is 2, plus 3 is 5. Y is 5. We'll look at that. Of course it is. There's 0, 5 right there. So just by paying attention to what happens to my graph when I add or subtract numbers inside the absolute reference and outside the absolute reference, then I can predict what's going to happen to my parent graph. So once I have a good idea of what my parent graph looks like, this is called translating. I can just translate my new graph just based on what I'm doing with numbers inside here. Easy peasy lemon squeezy, right? Right. All right, let's do another one. Let's say y equals the absolute value of x plus, I'll just say 1. I don't want to draw too big a graph. Minus 2. All right. Well, as always, I will start with just my good old Cartesian plane here. Okay, and as you recall, my parent graph looks like that. There it is. That's y equals absolute value of x. So what have we done to the parent graph by adding these numbers in here? Well, I added a 1 in here. And when you add a number inside the absolute value, you're shifting the graph to the left. Adding a number shifts to the left. Subtracting a number shifts to the right. So adding this, that means this point that was right there has now been moved 1 space in the left direction. But at the same time, I'm subtracting 2, and we know that affects the graph up or down. If I subtract 2, I move down 2. So this point that was here has now gone to the left 1 and down 2. So that point that was there has been moved to the left 1 and down 2. Left 1, down 2. That means this new graph will look like this. Well, there you go. It's that easy. Yes. Yes, it is. Now, let's look at let's double check a few points. The more interesting points are often where it crosses the axes, okay? So this point right here, when x is 0, 0 plus 1 is 1. Absolute value of 1 is 1. 1 minus 2 is minus 1. That's that point right there, 0 minus 1. Okay? Up here, when x is 1, I have 1 plus 1 is 2. And what was I going to say? Something pretty important. Yeah, absolute value of 2 is 2. 2 minus 2 is 0. So that's how we get the point right there. Now over here, well, you can see that when x is minus 3 plus 1 is minus 2. The absolute value of minus 2 is positive 2. 2 minus 2 is 0. So that's why I crossed 0 again over there. But I don't need to plot those points, because now I know I can just shift my graph up, down, left, right, higgledy-piggledy. Okay? Let's see what we got here. So I can make that, I'm using nice simple numbers because it helps me to draw the graph pretty easy. But let's say I had y equals the absolute value of x minus 17 plus 22. Okay? Well, there is my Cartesian plane, x and y. Just this time, I'm not going to draw it in. I want you just to visualize what your parent graph looks like, okay? And what will happen to said parent graph? Well, by subtracting a number inside the absolute value symbol, by subtracting a number, that means I move that many spaces to the right. So this graph, which was here, is going to go over 17. And by adding 22, that means that the whole graph goes up. So this point that was here at the origin in our parent graph, 0, 0, is now at 17, 22. So that means this new graph is just going to go woof, woof, just like that. It did look like that, but that moved it up and over. I know what you're thinking, gee, that's really easy. Well, it can get a little more difficult, because this now explains what happens to our parent graph whenever we add or subtract a number within the absolute value and add or subtract a number outside the absolute value. But what if we're multiplying something? Consider this. Here's our good old parent graph. What happens if I do this? If I multiply that by a number outside the absolute value reference? Okay, well, let's see what happens. Once again, I'm going to draw my absolute value here. And there we go. And you can recall what these numbers are. That's 0, 0. That's 1, 1. That's minus 1, 1, 2, 2, minus 2, 2. Okay. So now let's see what happens with my new graph because of that multiplication there. So 0, 0. When x is 0, y is 0. Yep. X is 0. Oh, sorry. X is 0. Y is 0. No change there. When x is 1, y is now 2. Now, isn't that interesting? X is 1, y has moved up 1, 2. Huh. When x is minus 1, the absolute value minus 1 is 1. 2 times 1 is 2. This moves up 2. Look at that. When x is 2, 1, 2, minus 1, 2, 2, and minus 2. When x is 2, absolute value of 2 is 2. 2 times 2 is 4. When x is minus 2, absolute value minus 2 is 2. 2 times 2 is 4. There we go. And that means this point that was at 2 is here is now up at 4. 1, 2. 1, 2. So the graph still starts at the origin, but you can see that it's going to go up faster. Now, different teachers have different ways that they call this. Some would say this, you're stretching the graph in the y direction. Some would say, well, no, you're compressing the graph in the x direction. But you need to be aware that by multiplying out here, that's going to cause the graph to go up at a faster rate. In fact, it goes up twice as fast, doesn't it? 2 times. If I multiply this by 100, it go up 100 times as fast. Okay? Just depends on how fast you're going to take all these x values and double them or quadruple them or triple them, whatever. Okay? So multiplying a number outside the absolute brackets just caused my graph to go up that much more quickly. Okay? I would say that that compresses it in the x direction. It takes those guys and it squeezes them in, so now they're a little closer together. You squeeze them so they go, okay? All right, there we go. Now, what happens though if I multiply a value inside there? Wouldn't that be interesting? Okay? Wouldn't that be interesting? Let's see. All right, oh wait, no. Before I multiply a value in there, let's multiply this value by a number that's less than 1. So let's look at what happens when I have this graph right, this equation right here. Y equals 1/2 the absolute value of x. All right, well, let's look at my parent graph again. Here we go. There we go. Now I'm gonna make this parent graph a little larger so I can illustrate my point better. There's 1, 1, 1, 1, 1, 1, good. There is 2, 2. So this is my parent graph. This graph, as you recall, is y equals absolute value of x. Splendid. Now, what happens then to this graph when I put a number that's less than 1? We saw if I put like 2 there, it just causes that graph to grow even faster. Well, you can probably guess what's going to happen now. Okay, so let's look at some values here. When x is 0, well, 0 times 1/2 is still 0, y is still 0. We're still right there. Okay, but now when x is 1, absolute value of 1 is 1. 1/2 times 1 is 1/2. That means this point that was there is now there. Get that, would you? Look at that. And this graph here, if x is minus 1, okay, now the absolute value minus 1 is 1. 1/2 times 1 is 1/2. That is right there. And let's see what happens here. When x is 2, 2 times 1/2 is 1, so this is just going to be right there. And x is minus 2. Minus 2, the absolute value of that is 2. 2 times 1/2 is 1. That's going to be right there. That means this is going to go like that. So you can see that flattens everything. Okay? So to my mind, this is stretching the graph. This stretches the graph. This shrinks the graph. Okay. When I put a multiplier outside the absolute reference, that compresses the graph. It causes it to go up faster. If I put a value that's less than 1 out here, that will compress, or stretch the graph rather, make it go up less fast. And that makes sense, doesn't it? If I have a number here that multiplies everything, it's going to go up that much more fast. If I have a number here that halves everything, it's going to go up half as fast. That, to me, that's self-explanatory, right? Right. Okay. Now, what happens then, however, if I have something like this? Y equals the absolute value of 2x. Huh. Does that change anything? I wonder if that changes anything. Let's see. There's my Cartesian graph. Good. Here's my parent graph. It goes like that. Right. Yeah, there's my parent graph. Again, y equals absolute value of x. Okay. Now let's see what happens here. Let's plot some points for our new graph. Let's see what happens. I'm going to go like this and like this. Okay. X is 0. X, y. When x is 0, well, 2 times 0 is 0. That's not 0. Y is still 0. So we're still right there. No problem there. Okay. When x is 1, well, 1 times 2 is 2. Absolute value of 2 is 2. So y is just, when x is 1, y is 2. Well, isn't that interesting? 1, y is 2. I did not see that coming, did you? No, of course not. When x is minus 1, well, minus 1 times 2 is minus 2. The absolute value of minus 2 is 2. Well, that looks like there. In fact, I don't think we need to beat a dead horse here too much. Does not this graph look just like that graph? Yes, it does. So whether I put a multiplier outside or inside the graph for this example makes no difference. And the reason why is because, as I'm sure you know, the absolute value of 2x is equal to the absolute value of 2 times the absolute value of x, and the absolute value of 2 is just 2. That means this and this are the same. Okay? This and this, same thing. Sorry, I can get in the picture here. That and that, same thing. Okay? All right. Now, finally, one last item here. What if I have a negative outside the absolute value? Well, here's my XY coordinate plane. All right. So here's my parent graph. Well, by having a negative outside our, like I'm trying to say, absolute value there, that's just going to make every y value that was positive now negative. That means this point here that was 0, 0, is still going to be 0, 0. But this point here that was 1, 1 is now going to be 1, negative 1. This point here that was 2, 2 is now going to be 2, negative 2. Putting a negative out in front there causes what we call flipping the graph. It flips it. Everything that was positive is now negative. So let's run a synopsis of what we have so far. Okay? If I have some absolute value reference, let's say I have A times the absolute value of X plus or minus B plus or minus C. Now, let's look at A. If A is negative, in other words, A is less than 0, then that will flip the graph top to bottom. So flip the graph. If A is greater than 1, that will cause it to, the whole graph to go up faster. So that means that will compress the graph, cause it to go up more quickly. If A is less than 1, so it's a fraction, then that will stretch the graph and cause it to go not up quite so fast. It's going to stretch it out more left to right. That's what A does. B. If B is positive, in other words, it is greater than 0, then that will shift the graph to the left in the negative direction. If B is less than 0, that will shift the graph to the right in the positive direction. So if B is positive, it shifts to the left. If B is negative, it shifts to the right. And C, if C is positive, in other words, C is greater than 0, that takes the graph that up. That shifts, moves the graph. Some people would say shift as well. Moves it up. If C is less than 0, that moves the graph down. Your teacher might have other words she uses here, but the principle is always going to be the same. So, having said all that, then, let's look at a more complicated one that involves all of these things, shall we? Okay, hang on, I need to grab some paper. All right, then. Let's do this. Let us graph y equals negative 2 absolute value of x plus 3 minus 1. Okay. Let's graph that right here, huh? Now, I'm going to lightly sort of pencil in my parent graph. This is y equals absolute value of x. That's not my final answer. My final answer will be in blue. So I'm going to graph this. Now, I could graph it by drawing a little table and plotting a bunch of points, but I don't have to do that. I'm going to use my knowledge of what happens when I just add or subtract numbers with my parent function. And what this tells me is that it's going to be flipped, the negative. So this graph right here is going to be flipped. Okay. It's going to be compressed. It's going to be shifted 3 units to the left. So shift 3 to the left, and it's going to be moved 1 down. All right, so I'll just start with this point right here. This point here is not going to be affected by that, but it's going to be moved 3 to the left, so that's 1, 2, 3, and 1 down. So that point right there at the origin is now right there. And since this is flipped, that means this graph is now going to go this way. Since it's compressed, it's going to be a little tighter V. Otherwise, it's going to stay the same. There you go. Done. Done. I just drew that graph. Now, if you want to get persnickety about it, you can actually see where this crosses. When x equals 0, let's see what happens. We have 0 plus 3 is 3. Absolute value is 3 is 3. 3 times minus 2 is minus 6. Minus 1 is minus 7, so it crosses here at 0 minus 7. There you go. But I don't need to plot any points to get a very good idea of just exactly what that graph looks like. Okay, let's do one more here. Let's say y equals, let's do a positive 4. No, let's do a 1/4. Ha ha! And let's say x minus 4. Yeah. Plus 4. There you go. I just made that up right off the top of my head. If you couldn't have done that, don't worry. I'm professional. All right, so we know what our parent graph looks like. You have a good picture of that in your mind. Let's see what's going to happen. This 1/4 is going, there's no flipping because there's no negative involved, so that's not going to come into effect. But 1/4 will cause it to go up less quickly. That means it's going to stretch our graph left to right. So this graph is going to be stretched left to right. Okay. This minus 4 in here is going to cause it to be shifted. Since that's minus, it's going to shift in the positive direction. So it's going to go 4 to the right. And the plus 4 out here is going to cause it to move 4 in the upward direction. So that means this graph, which normally would have looked like our parent graph, is going to be squashed, stretched out, and it's going to be, you recall it was here, it's going to be over 4, 1, 2, 3, 4, and up 4, 1, 2, 3, 4, and squashed by quite a bit. It's going to go up 1/4 of the speed it used to, sort of like that. And again, if I wanted to get fancy, I'll go and figure out what that value is right there when x equals 0. X minus 4 is negative 4. The absolute value of negative 4 is 4. 4 times 1/4 is 1. 1 plus 4 is 5. So that point right there would be 0, 5. And there you go. I hope that helps. Now, I know what you're thinking. You're thinking, wait a second. What if something looks like this? Y equals, let's say, 1/2 the absolute value of 2x minus 3 plus 2. I know you do these simple numbers, but it doesn't matter. The principle's the same. Looks like I've thrown you for a loop there, huh? Interesting. Interesting. Okay. Well, let's just see. We know quite a few things here. Okay? And we know that it's not going to be flipped. We know that the 1/2 is going to cause it to go up squished fashion here. Okay? And the plus 2 is going to cause the graph to move up too. But what happens in here? Well, you will recall from before that y equals the absolute value of 2x is the same as saying 2 times the absolute value of x. Right? So in a case like this, what would have to happen here is that I would factor a 2 out of this. So this equation would now read y equals 1/2 2 times x minus 3/2 plus 2. Okay. I'm going to move this over here to make it more clear. So I've just factored the 2 out of that, so it says y equals 1/2 2 times x minus 3/2 plus 2. So I haven't changed anything. I've just multiplied that. I just factored the 2 out of there. Okay? Well, I can now do the same thing I did here. I can write this as y equals 1/2 the absolute value of 2 times the absolute value of x minus 3/2 plus 2. Well, the absolute value of 2 is just 2. 2 times 1/2 is 1. So now this is just 1 x minus 3/2 plus 2. So the upshot of it is that all this graph is going to do is be shifted minus, or 1.5 units. It's going to be shifted 1.5 units to the right, and it's going to go up 2. So my parent graph was there. It's going to go minus 1.5, 1.5, and up 2. Going to be right there. And then there's nothing else going on with it. It'll just go like that. Okay. So don't let them fool you with stuff like that. No, don't let them do that. Do not. Do not. All right. Visit me again when we'll talk about absolute value inequalities. Yes, that's exactly what we'll do. Thank you very much.